Children, today we are starting up with a very important chapter, what we call as dual nature of matter. In this case, we'll talk about the light waves. If you might have seen the light waves already, we have seen the light waves is what exactly light waves is depending upon the wave theory. So far, we have done the wave theory, and we had very solid phenomena to prove for the wave nature. We had the diffraction phenomena, we had the polarization phenomena. But when we talk about the particle nature of the light, then here we comes with the condition that it shows two different properties. It has got the particle nature as well as the wave nature. So today's class in the dual nature of matter, we will be doing with the double role or the different aspects of the nature of light. That is the light. It has got the wave nature as well as it has got the particle nature also. When we talk about the particle nature of the light, so let us assume that this is the surface and lights are falling into it. Now, according to Planck's, one of the very renowned scientists, who gave the concept of this quantum mechanics, he told that according to him that the light falls on the surface in the forms of photon bundles of energy, and the bundles of energy is termed as photons, and this is termed as photons. Okay, now photons has got the energy E is equals to h nu. He told that the energy is not continuous, but rather the energy is discrete. And since it is discrete, so this value he gave is energy as equals to h nu. Here E is the energy, h is your Planck's constant, nu is the frequency. Right. Now this h is the Planck's constant and its value is 6.67 into 10 to the power minus 34 joule second. So this is the unit of Planck's constant. Okay. So this is what we have for the Planck's constant. And we have got nu is equals to c by lambda. C is the speed of light. C is the speed of light. And lambda is the wavelength. Okay, so what we have, we can put this into the equation h c by lambda. So this is what we are getting for the photons. Now there are some characteristics of these photons. If we go for the photons momentum of the photon, then momentum of the photon is, we have the formula, or we have the formula P is equals to, we can very well write P as equals to the mass into velocity, but at the same time, we from the Einstein's energy equation, we have got E is equals to mc square and E is equals to h nu. So it means mc square is equals to h nu. So if I have to m is the kinetic mass of photon. Kinetic mass of photon. The rest mass of photon is 0. So we have got m as equals to h nu by c square. Okay, so these are the things that we need to know what exactly we are talking about, the photons and this kinetic mass and all. So that is what we are talking about, the wave nature. Now we have the wave nature, and the very important relation that we have for the wave nature we talk about is the photoelectric effect. Photoelectric effect. Now what exactly is photoelectric effect? Suppose if you have taken a metal surface and light is allowed to fall on it. When the light falls on the metal surface, then what it does, it takes the electron out of the metal surface, and as the electron starts flowing, there is a potential difference developed, and this potential difference, what we call, is creating the photoelectric current. Okay, so ultimately when the lights are falling on the surface, it is giving what? It is giving you the current. And since it is just because of the light which is incident on the surface, so it is called photoelectric effect. Okay, now this is the phenomena for what we call the photoelectric effect. Einstein worked much on this, and he took the help of the Planck's theory, that is the energy is discrete, the quantum theory, and for this Einstein was given the Nobel Prize. Then he got the Nobel Prize based on the photoelectric effect, and he gave the relation according to Einstein. If h nu is the amount of energy which is falling on the surface, then it is h nu is equals to W plus half mv square. What he gave the condition that when the light of wave energy, that is h nu, is falling on the surface, then a part of it is being used to raise the electrons, to pull the electrons out of the metal surface, that is given by work function w, and at the same time some energy is given so that the electrons keeps moving. So here w is the work function. W is the work function, and this is equals to h nu naught. Nu naught is the threshold frequency. Okay, so nu naught is the threshold. So let us first understand what is work function. Work function is the minimum energy required by the electron to get out of the metal surface. This is the minimum energy requirement, and generally we measure work function in terms of electrovolt. Now nu naught is the threshold frequency. We call it as the cutoff frequency also, because generally whatever light is incident on the surface, not necessarily it is pull the electrons out of the surface. There is a certain requirement, and this certain requirement is what we call the certain requirement of frequency is known as cutoff frequency or threshold frequency. If the frequency is less than this, then definitely the electrons will not be ejecting out of the metal surface. So this is what we call the threshold or cutoff frequency. It is also known as cutoff frequency. So once the electrons are out, then definitely they have some energy with it, and this is given as half mv square, and this half mv square is equals to ek, that is the kinetic energy, and sometimes the kinetic energy is given as ev naught. V naught is known as stopping potential. Stopping potential. Actually, it is being seen that if when the experiment was done on photoelectric effect, when the plate was given zero potential, then the photoelectric current was not zero. Still, the current was seen. So, when the potential was taken to negative, when the potential was taken to negative, then it was seen that for the negative value of the potential, the photoelectric current becomes zero. So V naught is what we call the stopping potential, is that potential, negative potential, rather it is a negative potential for which there is no photoelectric current. Okay, so that is why it is termed as stopping potential. I hope you must have understood this. Thank you for watching. So this is what we were doing with the photoelectric current. It was general introductory class on the photoelectric current. Next class we are going to do with the laws of the photoelectric current, and we'll learn more on it. Thank you for watching.